Okay, one of the problems that gives everybody, that gives a lot of people trouble is adding two fractional expressions. Remember, to add two fractional expressions, you've got to have a common denominator. Okay, and the way I really want you to do this is to write this out as follows. You've got 1 over x minus 2 times x minus 5 over x minus 5. That's going to give you a denominator of x minus 2 times x minus 5, right? And then 1 over x minus 5 could be multiplied by x minus 2 over x minus 2. And now the two denominators, except for the order of your expressions, are identical. Now, since the denominators are multiplied, when you multiply, well, let's multiply the first fraction and multiply the numerator times the numerator. Now, if you do this completely, you're going to write that as 1 times x minus 5. Because it won't always be 1 here. It could be a different number. So you want to write that number down, even if it's 1. Then we multiply that, or we write the denominator as x minus 2 times x minus 5. And then this is 1 times x minus 2 over x minus 5 times x minus 2. Well, x minus 5 times x minus 2 is the same as x minus 2 times x minus 5, because multiplication doesn't, the order doesn't matter. We say multiplication is commutative. So the first equation becomes x minus 5 over x minus 2 times x minus 5. And to that we add x minus 2 over x minus 2 times x minus 5. I've just reversed the order of these two factors here, so they look the same. Okay. Then I can add, I have the same denominator, now I can add the numerators. Now adding that, I get, this gives me 2x minus 7 when I have these two numerators. And my denominator is x minus 2 times x minus 5. Now, ordinarily, if possible, I'd factor the numerator to see if any factors in the numerator match factors in the denominator. In this case, numerator doesn't factor, just a linear expression. Okay, I could factor the 2 out. That wouldn't do me much good because we still wouldn't match either of the factors of the denominator, so nothing would divide out. So that would be an acceptable answer, and I usually want to see the answer with the denominator factored. But then it's also good, right? This is with the denominator multiplied out, and of course you would use the distributive law to multiply the two binomials. Okay, but you come out with this if I did it right in my head. Okay, my head's pretty unreliable. That's a seasonal thing. Usually it is this time of year. Okay, so anyhow, that's how you do number 3. Number 4, you might make yourself a note. Well, I can disclose the number 4 just for contrast. We have 1 over x plus 2 times 1 over x plus 3. Okay. Well, this is multiplying. We're multiplying two fractions, two fractional expressions. We multiply the numerators and we multiply the denominators. So this is then just 1 over x plus 2 times x plus 3. Of course, we can multiply that out. Get this. So the multiplication is much simpler than the addition. We don't have to mess with a common denominator. We just multiply the numerators and multiply the denominators. you can't do that with addition. You can't just add the numerators and add the denominators. It comes out without anything much in common with the original expression. Okay, so let's see if there are any questions here. Okay, now, remember, we can only add fractions if they have the same denominator. How are you going to get the denominators to match? Well, you got a denominator of x minus 2 and a denominator of x minus 5. You get a common denominator. Well, a common denominator, well, the product of your denominators is always a common denominator, okay? Now, a lot of times it's simpler than that, but in this case, the common denominator would have to be x minus 2 times x minus 5. To get the denominator of the first fraction to be x minus 5, I've got to multiply the x minus 2 by the x minus 5 denominator. But I can't just do that without also multiplying the numerator by x minus 5, because the way I've got it written here, what's x minus 5 over x minus 5? That's 1, isn't it? So I'm just multiplying this by 1, which doesn't change its value. Multiplying by 1 doesn't change the value of the expression, but it can change the form of the expression. And in this case, it does change the form, so that now I'm going to have x minus 2 and x minus 5 in the denominator. Of course, we got to understand that multiplying two fractions, as we did over here, you multiply the numerators and multiply the denominators, okay? So we multiply the numerators, we multiply the denominators, and now we've got a denominator of x minus 2 times x minus 5. Over here on the x minus 5, well, to get the same denominator, we multiply by x minus 2. But again, we've got to multiply by 1, so we've got to multiply by x minus 2 over x minus 2. And then when we multiply numerators and multiply denominators, lo and behold, we've got the same denominator. Now, these two factors are in different order here than they are here, but the order of multiplication doesn't change the result. So I switch the order so everything looks good. And now I see that I clearly have the same denominator. So now I can just add the numerators. Now this goes back to, if you're having trouble with it, go back to adding simple fractions, 5/8 plus 3/7. Okay? And make sure you totally understand that so that this makes more sense. Okay? Okay, well, let's move on. Okay, number 6. You might or might not have seen this SQRT, but it stands for square root. Okay? And you might see that on the test, so make sure you make a note of the fact that that means the square root. Now, normally you're not going to have a bunch of 1s here. Okay? So let's do this instead. Okay? So I'm going to kind of cross this out because it's not the greatest example. It's what the program spit out. See if it's doing that on some of the other problems. Yeah, you're still getting a 1 there. And of course, it was my program, so since I spit it out, it usually doesn't come out that bad. Okay, too many 1s. Okay, anyhow, let's do this. Okay, now what's the square root mean? Well, it means what you multiply by itself to get this expression, right? Okay, so square root of 3x cubed y to the 6th equals the square root of 3. The square root of x cubed times the square root of y to the 6th. Okay. Square root of 3 is an irrational number. You can't do anything about that, so it's just going to stay the way it is. Now, the square root of y to the 6th. Let's look at that first, and then we'll look at the square root of x cubed. Okay? Square root of y to the 6th is y cubed because y cubed is y to the 3 plus 3, which is y to the 6th. Okay? Now, square root of x cubed, we could say that's x to the 3 halves, because x to the 3 halves times x to the 3 halves would be x to the 3 halves plus 3 halves. 3 halves plus 3 halves is 3. But we're not going to do that. We're going to write this as the square root of x squared times the square root of x. The square root of x squared is just x, because x times x is x squared. So we can write it that way. So it's the square root of 3 times x square root of x times y cubed. Looking at this expression, it's going to be square root of this, square root of this, square root of this. Square root of 3 is just square root of 3. Square root of x cubed, we can write as square root of x squared times x, because now we can write the square root of x squared as just x. But we still have the square root of x left over. And square root of y to the 6th is y cubed, because that's what you'd multiply by itself to get y to the 6th. So it equals this. And then we generally write this with the square root of the number out in front. And then the xy cubed, then the square root of x in the end. That's not necessarily the most standard form. And we could write this down as xy cubed times the square root of 3x. You want to do the algebra. Okay. So there's that one. See if there are questions. Okay, so number 7, we use the SQRT, and I typed it out. Okay. So you got to know that that translates to the square root of 4x minus 1. And then plus 40 equals 27. Now, when you solve an equation involving the variable in a square root, just as if you're trying to solve an exponential equation or logarithmic equation, you want to isolate that square root on one side before you convert the form. Okay, and you're going to convert the form just by squaring both sides. But let's see how this works. So we get subtract 40 from both sides. We get the square root of 4x minus 1 equals negative 13. Okay. Now there's a problem with this. There's no solution. It's never negative. Okay. So right there. That one turns out to be kind of easy if you just put it into the form with the square root on one side. Now let's do one where the square root doesn't come out negative. Yeah. Okay. We get this, subtracting 15 from both sides, which gives you the square of 4x plus 1 equals 12. Okay. Now, how do you get x? You square both sides. If you square 4x plus 1, you get this. And now I can solve for x. So I'm not going to run through the solution for x, but I'm just going to indicate. Solve for x. Well, you're going to subtract 1 from both sides, you're going to get 143. You're going to divide that by 4. Put 3 dots here and just tell you that x equals 143 over 4. Okay. Now notice one thing. If I square both sides of this, I get something that I can solve. I get 4x minus 1 equals 169. So 4x would be 168. And x would be 42. Okay? But the square root of 42, well, the square root of what I get here, well, 4x minus 1 would be 4 times 42 minus 1, right? Oh, wait a minute. I said x was 169, 168. I subtracted 1 when I should have added 1. It's 170. So x would be 42 and a half. If I square both sides of this, I get a perfectly nice solution. X equals 42 and a half. But if I plug 42 and a half in here, I get the square root of 169 equals negative 13, which isn't true. Square root of 169 is 13. It's not negative 13. Okay? So I'm just saying this. You want to be careful about extraneous solutions. You always want to check your solution when you're squaring both sides to make sure you don't get an extra solution that doesn't work. You want to make sure your solutions work. It's very important when you're squaring both sides. So I'll just toss that out. We don't want to spend a whole lot of time on it. And I don't really want to write it out because we have several problems that we need to get through. Okay. Okay, now number 8. Domain and range of y equals the square root of x minus 8. Okay. Okay, we got y equals x minus 8. We want the domain and range. It's all the values of x that work. Okay. Can you give me a value of x that doesn't work? Okay, well, X can't be 0, since the square root of 0 minus 8 is the square root of -8, which doesn't exist. There's no number you can multiply by itself to give you a negative. Okay. X can't be any number. It makes X minus 8 negative. Okay. So X minus 8 has to be greater than or equal to 0, so you can use the square root. And that's a very simple inequality. Just add 8 to both sides. Add 8. Recognize let's go to the right 0. Okay. So X has to be greater than or equal to 8. Now we can graph that on another line. Here's the x-axis, here's 0, and here's 8. So our domain is all values, including 8, so we put a closed dot here, and all values greater than 8. Okay, 8 and all values greater. There's the graph. Okay, now the range, well, X can be any number greater than or equal to 8, so you can have the square root of any number at all, any positive number. There's no limit to how big X can get, there's no limit to how big this can get. Okay? So, intuitively, I can be square root of any number. Now, I can actually solve this for X. We square both sides, we get y squared. Equals X minus 8, so X equals y squared plus 8. This means for any y you might want this to equal, you just square that and add 8, and that tells you what X has to be. So the range would consist of any positive number at all. Well, yeah, for any value y, you can find a value of X that gives you that value of y. Okay, for any positive value of y. I don't have room to write it all out, but for any y greater than 0, X equal to y squared plus 8 will give you that value of y. So if you want to get y equal to 7, 7 squared plus 8 is 57. if x is 57, 57 minus 8 is 49, and the square of 49 is the 7 that we were looking for. Okay, maybe have to digest that a little bit. I could write out more, but you check your text and so forth. And the open math problems you did back early in the semester. Okay? You get more explanation, but that's the mechanics of it. And if we had more time, we could digress a little further into this. And if I had more boards, there's a little more to write out, but I'm going to just leave it the way it is. Okay. Now, I think we have number 9 on our list. Okay, so number 9 gives you a function f of x equals 4 over x minus 2. Ask you to do f of 6. Well, we should know if we say f of 6, and we've got the rule for f of x, then we just let x be 6, which would give us 4 over 6 minus 2. Okay, well, that's 2/3 times 2, which is 2/3, minus 6/3, which is negative 4/3. And I'm not going to go into detail. Just notice that negative 2 is the same as negative 6 over 3. Now I've got the same denominator, so I can just add my numerator. F of 6 plus f of negative 5 equals negative 4 over 3 plus, well, f of negative 5, I can write out f of 6 because I've already calculated it. F of negative 5 would be 4 over negative 5 minus 2. And if you simplify the fraction, that's going to be negative 4/5 plus 10/5. So negative 4/5 minus 10/5. So that'd be negative 14/5. So it's negative 4/3 minus 14/5. And that gets a little complicated. Your common denominator would be 15, so you'd have negative 20 and negative 42, which is negative 62 over 15. Now the fractions get a little ugly here, but that can happen. Okay. So that's f of 6 plus f of negative 5. Now, we know f of 6 plus f of negative 5. This is, if I did my arithmetic right, it's negative 62 over 15. What's this? Well, 6 plus negative 5 equals f of 1, which is 4 over 1 minus 2, which is 2. Negative 62 over 15 is not negative 2. So f of 6 plus f of negative 5 is not equal to f of 6 plus negative 5. This illustrates something that I emphasized in class. Function notation doesn't distribute over addition. This is not multiplication, okay? Multiplication distributes over addition. Don't distribute function notation over addition. That's the lesson of this problem. And of course, the problem is also an exercise in evaluating functions. And, got to do some fractions too. So that's kind of worth digesting. The main lesson of this problem is don't treat function notation like it's multiplication. It's not. Okay. So I'm going to actually add that. It's a common mistake that people think that's okay. At least get to the ones where you both greater than 2. Okay. So it'll be 17 and 18. We'll do 18 first. Okay, I accidentally left the recorder on, but just to be sure that we emphasize the point, we can't assume that f of a plus b is the same as f of a plus f of b. You see that it didn't work here, okay, for this function. And it won't work in general unless you happen to have a linear function. It would work for a linear function, but just don't ever assume that you can do this, okay? Even if you got a linear function, don't assume that you can do it. Just work it out, see if it works. Okay. So number 18. Basically, it's asking us to graph y equals x squared plus 7x plus 12. Well, I'm going to use this factors in the x plus 4 times x plus 3. Got a question here. Okay. Somebody pointed out that on some of the other versions, the question is pretty different, gives you different information. So I'm going to do that too. Sure to have time to do it. We'll see how long it takes to do this, but we spent a lot of time. I'm going to go through it rather quickly just to refresh you on what you need to know. Okay. Now I said that I'm going to use the quadratic formula to find where y is 0, because usually you're going to have to do that unless it's contrived to be factorable. In this case, it was factorable, but you can't count on that. Okay. Now, comment at the end, other factor would have given us the same result. But to graph, find the zeros. Y-intercept. Axis of symmetry. And the vertex. Start with a quadratic formula. Y equals 0 if and only if x equals negative b plus or minus the square root of b squared minus 4ac all divided by 2a. And I'll caution you, I'm not going to give you a formula sheet, okay, in a pre-calculus course. Now, this is the core course, so if you take the exam for this course, which you really don't need to do if you're sure you're going to pass pre-calculus, okay? But it probably should take both, just to be careful. And yeah, make sure you're warmed up for pre-calculus. Take this one first. See what it is you come up short on, especially take it a couple of days before and have time to grade it and give you feedback. Could help you in your pre-calculus. And that's really the whole point of this course. Okay, so we start with the quadratic formula which says that. Okay, so I'm not going to go through the details, except to say that A is what's in front of x squared, which is 1, even if it's not written. If there's nothing written in front of x squared, it's 1. B is what's in front of x, it's 7. C is the 12. And Clear it out. Okay. Well, if we do the arithmetic, this comes out -7 plus or minus the square root of 1. Because 49 minus 48 is 1. And you can do the arithmetic. People do fun with the arithmetic. And just like that. Well, I can write this as -7/2 plus or minus 1/2. I don't have to write it this way. I can see that the numbers are going to be -3 or -4. No, I've not written it out like this, but I like this. 0 is a 1/2 unit right or left. So x equals -7/2. And that puts them at -3 and -4. Now, the reason I want to emphasize this form before I get the actual numbers is to show that I have -7/2, that's -3.5, that's on the x-axis. And then I add half to that or subtract half from that, which gives me a number half a unit to the right or half a unit to the left of -7/2. And that emphasizes the fact that x equals -7/2 is the equation of your axis of symmetry. So I'm going to put my x-axis here, my y-axis here. Why do I put a short segment of the x-axis to the right and a longer segment to the left? It's because these zeros are both to the left of the y-axis. They're both on the negative x-axis. I'm not going to need a lot of positive x-axis because I know in advance that the graph of this function just has the same shape as the graph of your basic squaring function. Nice, smooth parabola. Okay? I've got to know that in advance. But with all the work we've done about transformations and so forth, that should be very clear. But there's a whole lot of the picture of the course in this type of example. You get the horizontal and vertical shifts. And if you have a number in front of x squared, you get a vertical stretch. And you apply the whole idea of transformations to graph these. And on my final, I might ask you to demonstrate that. Okay? Don't know if you get it on the final from another course. But on my course, I'm going to ask you to understand that. Very possible. Okay. Anyhow, so here is -7/2. Well, then here would be -3, -2, -1. I'll make a note that -7/2 is -3.5. And now my zeros are at -3 and -4. My zeros. The axis of symmetry goes halfway between the zeros. The zeros are half a unit to the right and half a unit to the left of this number, right? So the axis of symmetry has to go through that number. And this emphasizes why the axis of symmetry is what it is. You can always memorize that the axis of symmetry is a -b/2a. which in this case would be the -7/2, which is here. Okay. If you happen to forget it, it's not that hard to reason out if you understand what the quadratic formula is telling you. So I do recommend that you try to understand it at this level of depth. But if you just memorize it, recognize it inside the quadratic formula, that's okay. Okay. You're more likely not to forget it if you understand what I'm telling you, though. Okay. Okay, just take that as advice and work it out, whether in your case it's good advice or not. Okay. If you find it's not good advice in your case, it's hard to understand, and just memorize it. Well, we've got a pretty good start on the graph. We know what our axis of symmetry is, and we know the 2 points on the x-axis. So what we don't know is how steep this thing is, whether it's a parabola that comes down very sharply and comes way down here, or one that comes down much more gradually, goes just a little below the x-axis and then back up. Well, let's then figure out the y-intercept. And I said y-intercept, there's only one y-intercept because this is a function. There's only one y value you can actually consider. Well, that's easy to take care of. You plug in 0 and you get 12. And you can see that you don't even actually have to write it out, although I advise you to write it out because it reinforces what you're doing. And people are still a little unclear on intercepts. Okay. So we plug it in, we get 12. Now we have quite a bit of information about our graph. Okay, we know that your y-intercept is 0 to 12. Now we have 3 points and at least one on each side of the axis of symmetry. That makes it easy to draw a nice smooth parabola. Now I'm not going to grade you in your artistry with a parabola, although if you really mess it up, I might take a point or two off. Okay. If you try to draw an upside down parabola through these 3 points, that's not going to be good. Okay. You can't get an upside down parabola. If you go upside down, you have to come back up here to get this one right. So it's pretty obvious where the parabola ought to be. So now we can sketch our parabola. Okay, well, going to have to come through here and go up here and be nice and smooth. I'd say it's going to come down kind of like this and kind of like this. That's reasonably symmetric, right? Okay. So I want to see reasonable symmetry. I don't want to see it too lopsided, but we're not artists. I'm certainly not. So I'm not going to have a real high standard there, as long as it looks like you kind of know what it ought to look like, and you don't have it wiggling up and down and stuff like that, like a higher degree polynomial, right? Should be okay. All right, so there's your y-intercept and your 2 points. Now the vertex, because we also want to find the vertex. Well, the vertex is on the axis of symmetry, so it occurs when x equals -7/2. Okay. So we plug in 7/2. The board's a little rough right here. So we just plug 7/2 into the function. And this gives us 49/4. This gives us -49/2, which is -98/4, giving us -49/4 for these 2 function expressions. And this is 48/4, So this gives us -1/4. You probably can't do that in your head. No reason you should. Okay, unless it's your hobby, or unless you're like me and don't like to sit up here punching buttons on a calculator and choose to just do it in my head so it'll be wrong. Okay. So now I know that this point here is at -7/2, -1/4. Furthermore, I now know that since I have a 1 in front of x squared, this is a transformation of my basic squaring function. And since the vertex of the basic squaring function is at the origin, and the vertex of this thing is at -7/2, -1/4, that this is just my basic squaring function shifted -7/2 unit in the x direction and -1/4 unit in the y direction. So that, now we're out of time, so I don't get to write all this out. This tells me then that y equals x plus 7/2 squared minus 1/4. Because that's what you get when you take x squared, shift 7/2 unit, -7/2 unit in the x direction. You replace x by x plus 7/2 for reasons that we discussed at some length. Okay. And then shift it down a quarter of a unit, which is pretty easy to understand since that's where the vertex is. Okay. This will shift the vertex of the squaring function to this point and give you the graph of this function. And this is the same expression you would get if you completed the square in this thing. But unfortunately, we don't have time to talk today about completing the square. If you remind me, we'll pick up on that next time. Okay? Or if I manage to remind myself, but good luck with that. Another class coming up. I don't have time to write a note. I don't know if I'm going to remember it.